Okay, ladies and gentlemen, this is the covalent drawing and structure summary. So this is a breakdown of covalent. This has more examples than the ionic because we did very well in the ionic formative. So with this, all right, the first thing we need to understand, okay, covalent bonds versus ionic bonds, okay? So in ionic, you must have a metal and a nonmetal. Well, covalent bonds are only made between nonmetals, all right? It has to be two or more nonmetals bonded together, okay? In an ionic, electrons are transferred. In covalent, electrons are shared, okay? And we represent that, all right, in a bond, okay? So it's shown by drawing a bond, all right? We should have no charges in our covalent bonds, all right? So covalent bonds are either polar or nonpolar, and we're going to talk about that next, all right? So how we know it's covalent? Two or more nonmetals bonded together, okay? Polar versus nonpolar is going to depend on our electronegativity as well. So, polar versus nonpolar. What does polarity mean? All right. So, if electrons are shared equally, all right, it's going to result in a difference of electronegativities that are very, very small. Okay. All right. So it's going to be less than 0.4. Okay, it's going to be 0.4 or less, and those are going to be our nonpolar bonds. Okay, our nonpolar covalent bonds, our electrons are shared equally. Our differences in electronegativities are very small as a result of that. Okay, our other option, okay, if electrons are unequally shared, then the difference in electronegativity will be larger. Okay, it'll generally be between 0.4 and 1.7. All right, and that's how we know if it's a polar covalent bond, okay? And again, we noticed this on Thursday when we looked at differences in electronegativity. Sometimes our polar covalent bonds will be greater than 1.7, but that just means that we have to make sure that it's two nonmetals, okay? If it's greater than 1.7 but has a metal, it's going to be ionic. If it's greater than 1.7 but has no metals, it's still going to be polar covalent, okay? It's generally between 0.4 and 1.5, okay? And that 0.4 we're going to categorize as nonpolar, okay? So we're going to keep this as nonpolar, okay? So it needs to be greater than 0.4. All right, so let's get into the practice. So the first practice I'm going to show you guys is I2, okay? So this starts similar to ionic drawings where you go ahead and just draw the Lewis dot structure, all right? The difference here is we need to examine the electrons that don't have a pair, okay? In the case of iodine, there's only one electron for each iodine that isn't involved in a pair. Those single electrons are the ones that are going to form our bonds. So iodine forms one bond with itself, okay? We need to show those leftover electrons. Otherwise, we won't show that iodine has a full octet for each, okay? So that should be your final drawing there, all right? Then we need to check our electronegativity, okay? Is this polar or nonpolar? So for iodine, it's 2.66 minus 2.66, all right? That is going to result in a 0 overall difference in electronegativity, which means that we are going to have a nonpolar bond on our hands, okay? Because it's less than 0.4, all right? If I were to make this in a model kit, it would look similar to this with both of our atoms on the same plane. So that means our shape is going to be linear, okay? We have no polarity, and there's not a symmetry found, okay? Our next example that we're going to do is phosphorus. So phosphorus, again, I'm drawing my Lewis dot structures. Phosphorus has 5 valence electrons, right? And we want to make sure that they're single before they mingle, okay? As a result for that, we know that phosphorus is going to make 3 bonds because it has 3 electrons that don't have a buddy. All right, so I'm going to circle my 3 bonds, all right? So this is what we would call a triple bond, which is the strongest of covalent bonds. All right, so when we draw this out, you're going to have P with 3 lines stacked up on top of each other to show the bond with our leftover 2 valence electrons for each phosphorus. All right. Again, we would do our calculation for our electronegativity, 2.19 minus 2.19, which results in a 0 overall electronegativity difference. This means that once again, this is a nonpolar bond, okay? Anytime an element bonds with itself, it's going to be nonpolar. All right, this shape again is going to be linear because if I used a model kit to show this, it would be two two elements on the same plane, no matter the way you twist it, okay? Our next example, we're going to do NF3, okay? So again, I draw my good old Lewis dot. Nitrogen has 5, fluorine has 7. So I know that I have 3 fluorines, so I need to draw my 3 fluorines with 7 valence electrons around each, okay? Nitrogen needs to make 3 bonds because it has 3 lone valence electrons. Each fluorine only needs to make 1 bond. So we're going to go ahead and show those bonds that are going to be drawn, right? And then I make my final structure with all of my leftover valence electrons that were not part of the bond, okay? Make sure you're not drawing the electrons that are part of the bond, okay? Then I need to calculate my electronegativity difference, okay? So I find my electronegativity for nitrogen and my electronegativity for fluorine, okay? So I'm going to put my larger electronegativity first and subtract by my smaller. This results in an electronegativity of 9.94, which is larger than 0.4, meaning that it's going to be a polar bond, okay? So we have to look at the structure. We got to look at the shape. First off, I'm going to draw how my polarity would look, okay? So, fast forwarded a little too far. I'm going to draw how my polarity would look, okay? So I draw out my structure again, all right? And I'm going to show the direction of my electronegativity. So fluorine is more electronegative than nitrogen, okay? So fluorine is going to have a slightly negative charge, whereas nitrogen is going to have a slightly positive charge, okay? So with that, all right, our electronegativity is actually going to be pointing towards our fluorine. So my arrows are a little backwards there. Okay, our electronegativities are going to be pointing towards our fluorine because it has a higher electronegativity, resulting in slightly negative charges on our fluorines and a slightly positive charge on our nitrogen. Okay, with that, we have an unsymmetrical structure because we have these 2 valence electrons on top of nitrogen, which are actually going to be pushing down, okay? That pushing down causes we already have polar bonds, but that pushing down causes the nitrogen to be slightly higher, meaning that they're not going to be on the same plane. So this is going to be trigonal pyramidal as opposed to planar, okay? Because of that push of electronegativity down on our fluorines, the push from our fluorines up on our nitrogen and the push from these 2 valence electrons down on our fluorines results in an unsymmetrical structure, which means it's going to be a trigonal planar, okay? So this you saw yesterday with your nitrogens and hydrogens, where you saw it kind of raised up off the desk, okay? Our last example that we're going to do is silicon and hydrogen. So again, I draw my valence electrons, Lewis dots. I pair up my unpaired, okay? So here, each hydrogen makes a single bond with it, all right? I go ahead and do my calculation. Hydrogen is 2.20, silicon is 1.90. My difference is 0.3. It's nonpolar, so it's less than 0.4. Symmetry, okay? I have 4 elements bonding with 1. It's always going to be tetrahedral. Okay, so our next example, we actually see that again, okay? So I do CH3Cl, can draw out my Lewis dot, all right? I bond my hydrogens, I bond my chlorine, I show my leftover valence electrons. I look at my electronegativity first for my CH, okay? That difference is only 0.3. It's going to be a nonpolar bond between my carbons and my hydrogens. However, my bond between my chlorine and my carbon is a 0.96. So that's a polar bond between the 2 of them. All right, so if I drew my polarity, there's not going to be polarity between hydrogen and chlorine, but there is going to be polarity pulling towards the chlorine, resulting in a slightly positive charge on our carbon and a slightly negative charge on our chlorine, okay? However, it's still symmetrical because we have 4 elements bonding with our carbon, okay? So it's still going to be a tetrahedral shape, even though we have that slight polarity as a result of our chlorine bonded, all right? So hopefully this helped with both polar versus nonpolar, covalent, and shape.